program a robot and write test cases for it. So here's where we're going to develop the model for that. And I don't have the robot here that we programmed last night, but essentially we want to come up with a physics model for an elevator with a motor on it. So let's start with our basic motor model. So this is a basic brushed DC motor. So you have an input and an output. So then you come through, a motor is modeled as a resistor and a generator. Okay. So the resistor is, if you think physically, the resistor is the copper in the windings has resistance. And so that's going to resist, voltage. So we're going to have the voltage across the resistor then, V equals IR, our famous Ohm's law. And then the voltage across the generator, V equals omega times our voltage constant. So this should be decently familiar. So if you put more voltage in, it's going to go faster. And then also more voltage, you can get more current. And the resistance is, we have copper in the windings. So we can put this together, and we have our motor equation. The voltage across the motor equals, actually, can you guys see, or do I need to be writing bigger? I got a thumbs up in the back. Great. Actually, hold on, let me make sure I got KV the correct direction. KV. I think it should be divided by KV. Yep, sorry. I'm trying to adhere. The physics works out if you do KV or 1 over KV, but if we use the right conventions, it will match what's used in all the literature. So it's omega over KV. So let's, so then there's one other equation, which should also be useful. So a motor is an electromagnet. So as you pass current through the windings, you're going to get more magnetic field. And so the equation so the torque out of our motor equals the current, and then it is times KT. So this says as we get more current, there's some constant proportionality correlating the current through the motor with the torque coming out. So we can pull some specs out of it. Let's pull some specs out of a motor data sheet, and we can go and try and derive some of these numbers. So I'm going to go, and I can't present to the projector and use the whiteboard at the same time, so I'll write up the numbers. But I'm just going to motors.vex.com, where you have all the is 5330. And then we can say stall torque. .4. And then our stall current is 131 amps. Over here. Okay, so I argue from these numbers, we can compute what KT, R, and KV are. So can anyone see how to get one of those numbers? Volunteer.
All right, when it's stalled, omega is 0.
Okay. So we're So then we can do this. So what would the other numbers be? So V equals.
Are they talking 12 volts?
Yep. So IR. Actually, sorry, what's I then at stall? So I then is our stall current, so 131 amps times our resistance, and then you said omega 0. So this cancels out. So there we go. So we have 12. So we got our first unknown. So from the data sheet, we can compute the resistance, which is pretty cool. So now let's pick another one. Yep, perfect. So we're going to pick another known operating point. So this is stall. So that will be, we'll have our stall torque, and then we know our stall current, and so we can compute KT. So that one's pretty straightforward. So KT would be stall torque over stall current. Okay, and then looks like we need KV next. Anyone? How about we take a quick motion? People can move down in the middle. We've filled the door. Great. Okay, so does anyone see how we can get KV? Should be pretty similar to how we've been doing the other ones. I got a hand, great. Yep, so we'll use the free speed operating points. What's that mean? Sorry, louder. So what's I when we're at free speed? No, that's stall. When you're at free speed, there is no current. No worries. That cancels out, plus omega. Well, we know of free speed. So this is our 5330. Where's our last one? There we go. So cool. So we've actually, so from our motor model and from the data sheet, which you can get these data sheets for all of our motors on motors.vexpro.com. It's actually pretty cool that somebody took the time to get all those coefficients for us so we can actually model this stuff nicely. We can get a pretty simple motor model. Yes? You just need to be consistent. I highly recommend doing all of this math in metric, but as long as you're really careful with your units, it will all work out. So a lot of the industry standard numbers are going to be more in metric. Or, well, this should be in radians. Volts is already metric. Yeah, sorry, radians per second. Thank you. So cool. Okay, so let me see if I can get this projector to work real fast, and we'll show you what stuff's online available. And then we should hook this motor up to an elevator, virtually. Is it gonna take? Oh, sweet, that worked. Okay. Come on. There we go. Okay, so motors.vexpro.com. Zoom a little bit. There we go. So here's where I was pulling those numbers from. So we can see here's our free speed for a sim, free speed for a mini sim, bag motor, all the various motors as you scroll down. We're pretty much ignoring the free current in this because it's compared to 131 amps, 2 amps isn't very much. And then our stall torque. So there's actually some more cool numbers we can go look at in here that someone's taken the time. So this is actually a graphical representation of this equation here. So we can see as the speed goes up, the current comes down, which is good. So with a fixed voltage, you can either have current or you can have speed. So that's essentially saying as you're going faster, you get less torque. and you get more torque off the line, which is what we see in the robots, which is good. And then here we can see torque. Torque and current are very closely related. So yeah, so this is pretty cool. We're able to see our motor model. And this should be done experimentally, this graph here. And then this is one of my other favorite ones. And this shows, so given different motor voltages, you get out different torques. And then Aaron tells me that when these lines fall down, that's when smoke comes out of the motor and it stops working. So you can see how long you can apply different currents to your motor before it starts blowing up. This one's super helpful for helping size motors. Cool. Any questions here? Yes.
So one of the things we're not considering is the impedance of the battery.
Correct. You can model that with another resistor. We're going to get reasonably close to this equation, and at some point you need to go out experimentally, and we're ignoring gearbox inefficiencies and a bunch of other. At some point you go run a test on your robot, and it will be pretty close to this, and then you can go fit some things, like model the extra resistance in your wire. What I tend to do is use the resistance as a lumped term for error. So if my robot's accelerating a little slower than I expect, I just up the resistance until it matches my model. You can run a little simulation and then have your robot drive the same thing and then see if they match. That gets you pretty close. Cool. Any other questions before I shut this down? Nope. Okay. Okay. So let's go model this attached to an elevator. Okay. So we'll do a free body diagram here. So just trying to describe, trying to break this apart. So we can model our elevator. Should be a pretty common elevator with, and we'll have a gear ratio attached to our motor. Okay. So we have our equation for torque. We'll do start my torque on the motor. So let's get torque on this shaft. So our gear reduction will increase the torque, and then our speed of the shaft is going to be, so here we're conservation energy. Our shaft's going to spin slower with more torque. Okay, and then we should break this down into the distance. Actually, I would start plugging this in a little bit. So then we have tau. I'm gonna, okay, we'll do this in more steps. And here, hold on, I need to divide by G here, sorry. And then we can go substitute current out. So we can get our voltage as a function of, yeah, our voltage and torque. So V. And if you see me doing the math wrong, please correct me. Okay, let's back through it. Let's try that again. I'm trying to get rid of motor torques and get us all into shaft torques so that we can then convert that eventually to, we just want to have our equation in the output terms, because we care about where the output is, right? Our elevator is at position 1 meter in the air, accelerating at this rate. We don't really care about what our motor's doing. So that's our end goal. Okay, so yep, you're right. Tow shaft. Put that in there. Hang on, where did I lose it? G, right? I can't. I'm having trouble doing math in front of an audience. Yep, G. There we go. Okay. So then, now we can substitute that in over here. Okay, so we're getting closer. So now let's convert this into our output here. So we have our shaft radius R. Let's apply an F. Okay, did I get that right? Okay. And then the other one we need, so that gets us in terms of a force. And then we need to get this angular velocity in terms of a distance, or a linear velocity. So assuming we're in metric, this will be 2 pi radians a second, pi times radius, or 2 pi radius should be your circumference. Sorry, V. Okay, so here we have given a voltage and a velocity, we can compute the force. So this is our differential equation modeling our elevator, which is pretty cool. So let's go over a quick numerical method for using that. We have computers, we don't have to do this all by hand. You can learn how to integrate that in a calculus class, which is pretty cool, but our goal here is to cheat. So let's talk about how to go from a velocity to a change in position. So if I have, so say I have this, from t0 to t1, we got constant velocity. What's the change in position? Yeah, velocity times time. So v times t, which is actually also this area. Okay. So say we did this, right? So say we went for a while, then we changed our velocity and went again. So we would just add in this little area here to get our change in velocity. So we can actually do this for arbitrary shapes. Say we have some curve. We can just fill this in with little squares. And then compute the size of the area of each one of those little squares. If you add those up, you get the change in velocity. So this is the same trick. If you do this again, we can go from acceleration to, yeah. If we do this again, we can get out the change in velocity given an acceleration. And we didn't do this very rigorously, but we can do this on a computer really fast. You can do this in Excel, you can write a little Python script, you can write Java, C++. So, cool. Any questions?
Would that be like, what type of math would that,
This is the broad field.
like this one specifically?
So this one is Euler integration.
Yes.
Squares. It's the first order integration. You can do better. There's a whole field on this. You can do better if you draw triangles here, right?
Yeah.
And then you can start to draw polynomials. You can get better and better. But I argue that for a lot of FRC, if you just make these really small and let your laptop run a little longer, you do pretty well. You can get yourself within 1% or 2%, and nothing else we do in FRC is within 1%. Yes? That's a great question, because it looks like I stopped early. So then we can grab our next equation, F equals mass times acceleration. And then we probably want to substitute this in. So they get voltage equals So then we can rearrange this equation to get acceleration as a function of voltage and velocity, which then lets us go integrate it as I just described. Thank you. Did people follow that? I see some nods. And this talk is being recorded here if you want to watch it again, and it's been recorded in other places. So this is one that's worth going through a couple times. And then I would encourage you to try this at home. You can do this in Excel if you want. You can do this in a little programming language. Yeah. I've been using 0.1 milliseconds. You want them to be just small. It's actually pretty cool. So as the way this works is as you divide these in half, your error should go in half. It should be a function of your width. So you can keep dividing them, and you can see if it's starting to converge on the same number. Oh. Okay, if there's no more questions, thank you. Yeah. Oh. So it turns out that's going to be a constant effect. Yeah, so if you have a PID loop, the integral term's just going to learn that. So it's actually easiest just to not model it for now. But if you're trying to do an actual simulation of a real robot and you want to see how gravity affects it, rather than do control loop design, then you can add it back in. Yeah.
Oh my God, would you add